Hi, I'm Daniel Chan from UNSW Sydney. Welcome to another adventure in pure mathematics. In this video, I want to revisit linear algebra using the perspective of abstract algebra. What we'll discover is that there's a lot of ring theory underlying your second year linear algebra course, and this is really lurking in the background when we try to teach a second year linear algebra. In particular, one of the things that we'll find is that there is one ring that rules all endomorphisms. Okay, so let's look at what linear algebra is about. It's really the study of linear maps, and in particular, the most important class of linear maps are those linear endomorphisms. So what do I mean by that? So that means just a linear map T where the domain and codomain are the same. So say T from V to V. So if you're studying this from the perspective of abstract algebra, the first thing you do, as always in mathematics, is to talk about, well, what are the notions of isomorphism and homomorphisms? Okay, so when we try to answer this question from the perspective of abstract algebra, we make this question precise by defining homomorphisms. So suppose we're given two such endomorphisms, T from V to V, and a T prime from V prime to V prime. So what should be a morphism between these two? So that just means a commutative diagram of linear maps, C-linear maps, of this form. In other words, you have a C-linear map phi from V to V prime, such that when you put the phi's here and the T and T prime here, when you go around this way, it's the same as when you go around that way. Okay, so now that allows you to compare two endomorphisms. Okay, and in particular, it will tell you what does it mean for two endomorphisms to be isomorphic. Okay, so if they're isomorphic, of course, you'd want this phi now to be an isomorphism. Okay, and this still to commute. And when you rewrite this commutativity condition, what you can do is you can re-express this T prime as going around the diagram this way. So it'll be phi inverse composed with this T, composed with this phi. And if you look at this expression, of course, hopefully you'll realize what this is about. This is essentially capturing the fact that you're looking at similarity. Okay, so this is the key point. We've got a notion now of homomorphisms between endomorphisms and also isomorphisms. Okay, so that's part one. If you want to answer this question, how do you study a C-linear endomorphism T from V to V? Okay, so the second thing that you need to do, now that you've made the question more precise, is you want to, up to isomorphism, decompose this endomorphism T into easily understood components. Okay, so let's see how you might want to do that, and I want to look at this a little thought experiment. Okay, so whenever you have an object in mathematics, okay, if it's complicated, then you start by looking at subobjects. Okay, so that's what we're going to do now. Okay, we're going to look at the question of, given some C-linear endomorphism T from V to V, we're going to try to find a subobject of it. So how do you do that? Well, where do we start? We'll just start by picking just some element inside V. Okay, that's a good place to start, V. And so what should be a sub-object in this case here? So I guess what you should have, suppose your object T is not this, in this diagram is given down here. Okay, so I guess to be a sub-object, if you want a sub-object of this T prime from V prime to V prime, what do you want? So I guess you want V to be a subspace of V prime, and then you'll need this T from that subspace back to itself, okay? And it should basically be a restriction of this T prime. In other words, you want some T prime invariant subspace. So here we want to try to look at some T invariant subspace. So how do we find that? Okay, we start with V, okay? So if this is part of some sub-object, okay, when we apply T to it, it should be inside it. So maybe when you apply T to it, you look at TV, this is not inside a part of this object, and I guess since you want a subspace, you'd look at the span of this, and suppose it's actually not in the span of this, okay? So that means that I guess if you want a sub-object containing this V, you'll need the span of both V and TV. Okay, so if it contains TV, the sub-object, okay, the T invariant subspace should also contain T squared V and also T cubed V and so forth. So if you look at the span of V, TV, T squared V and so forth, okay, you'll actually get a T invariant subobject. Okay, so why is that? Well, I guess the most important thing is to check that this is T invariant. If you look at the span of this, you just have to show that any element in the spanning set, okay, when you apply T to it, is in the span. And of course, for each element in the spanning set, right, if you apply T to it, you just get the next one in the spanning set. So this is stable, the spanning set is stable under T, and so is the span. Okay, so let's put some conditions now on V, which is the usual ones that you do when you look in linear algebra in second year, and suppose that the dimension of V is actually finite. Okay, so let's go through this procedure. What you'll find is that there's an infinite number of vectors here, so they can't all be linearly independent. Okay. Well, let's just suppose we start with this V, and TV is a linear independent to this V, and T squared V is linearly independent to this to the previous two, and we keep going until we get the first n of them are linear independent, but then Tn depends linearly on the previous ones. Okay, so let's just suppose this is true. Okay, so Tn depends linearly on those. So that means that Tn of V you can write as a linear combination of V, Tv up to T to the n minus 1 of V. Okay. Okay, that's great. And what about Tn plus 1 of V? Well, how do you get your hands on that? Well, what you can do is you can take this equation and you just apply T to it. And when you apply T to it, you'll get the next one along, Tn plus 1 of V. So you get alpha 0 Tv here, which is in the span of this. Okay, so let's write W as the span of these first n vectors here. Okay, so T of V is inside here. And when you apply T to this, you get alpha 1 T squared of V, which is also inside here. And all of them are inside there, except for, let's just check the last one. The last one's a little bit different when you check, because that's alpha n minus 1 times T to the n of V. T to the n of V, well, is that inside here? Well, we kind of said yes. We are assuming that T to the n V is linearly dependent on the first n terms. So that means T to the n plus 1 V is still inside here. And similarly, you'll see that actually this subspace here, of these n vectors, okay, is actually T invariant in this way, because when you look at the span of all of these, okay, which will be T invariant, actually you'll just get the span of the first n. Okay, so after you look at T and V and all the high powers of T acting on V, you'll stay inside the span of these first n vectors. Okay, so that's rather nice, because what that means is that in this finite dimensional case, you have a subobject, which is a span of the first of some first sequence of these vectors. Okay, and how many of them will depend on when you eventually get one of these to be linearly dependent on the first few. Okay, so that's rather nice, but we can actually say more. Okay, so what can we do? What I'm going to do is, and this is something that hopefully you remember from your second year linear algebra, is that this means that this T, okay, when you apply it to V at least, satisfies some polynomial equation. Okay, so let's write down the corresponding polynomial that you get. Okay, I'm going to replace the capital T's by little t's. Okay, so like at 2 to the n, and I'm just going to subtract alpha n minus 1, little t to the n minus 1, and so forth down the line to subtracting alpha 0. So there's my polynomial. And the key point of what's written here is that if I apply if I replace all the little t's with capital T's, and then apply that corresponding linear transformation, so it'll be a polynomial in this capital T now, to this V, you'll get 0. Okay. And what that means, if you use some basic module theory now, is the following. Okay. So if you look at C of T, what you can do is you can mod out by the ideal generated by this polynomial. Okay, and this is a vector space, right? And it's a vector space, and what's the basis? The basis is 1t squared up to t to the n minus 1. Okay. And what you can do is you can identify those basis vectors, okay, with v, tv up to t to the n minus 1v. And in this vector space, you can think about just multiplying by little t. Okay, this will take this back to itself, since this is an ideal. Okay, so this is going to be a linear endomorphism, C-linear endomorphism of this vector space. Okay, and what you find is that basically these two are isomorphic exactly by the isomorphism which matches the ith power of this little t to the ith power of the big T acting on V. Okay, so just to see why that's true, okay, so we just check that it does the same thing on basis vectors. So most of the time, what will you find? Most of the time you'll find that whether you use this big T or the little t, it will send one basis vector to the next one along. Okay, if you multiply the basis vector little t to the I by t, you get t to the I plus 1. So most of the time you just move it along. The only thing where something interesting happens is with this one here. When you multiply this one by big T, you'll get this linear combination over here. And also, if you multiply little t to the n minus 1 by this t, you'll get t to the n. And since we've modded out by this, you get exactly a similar looking thing, okay, except for you don't have the v's and the big T's are little t's. So that gives you the isomorphism between these two. Okay, so what's rather nice is that this subobject here, okay, you can capture, okay, just using this polynomial ring C of t, okay, and some more data, okay, so you need this p, okay, as well, and then that will give you what this is. So one of the things that's tricky when you study linear endomorphisms, of course, this vector space, there's lots of possibilities, but now we've kind of reduced what the possibilities for the vector spaces are by just looking at quotients of this CFT, at least to get these subobjects up to isomorphism. Actually, there's a lot more going on, so let me just tell you what's going on. And so the key point that I want to get across in this video is that this CFT, this polynomial ring over the complexes in this one variable, is the one ring that rules all endomorphisms. Okay, so this fact is getting us towards this. So suppose now you have any polynomial in little t, okay, then you can take that polynomial in this linear endomorphism t, and that will give you a linear endomorphism from V to V. And this essentially gives us a CT module structure on this V, okay? So we get a CT module structure on this V, so we need to know what that module structure is. Well, this is already an abelian group, so I just have to tell you how you scalar multiply by any of this f. And the way f acts on any vector v, this is any vector v now inside this big V, is you look at this linear endomorphism f of capital T, and you let that endomorphism act on this V. Okay, so this is the key point. Given a linear endomorphism, you actually get not just an action of this one operator, you get this whole polynomial ring acting on this vector space. Okay, and so this second upshot of what we've been talking about here is that the study of modules over this polynomial ring in one variable, little t, is equivalent to the study of C-linear endomorphisms. Okay, so really the best way to do linear algebra, okay, is actually to use module theory and to look at actually not just the scalar multiplication by a single operator, okay, this t or linear endomorphism, but by all these polynomials as well. Okay, so that will get you a lot more mileage. And the reason why is that in a certain sense, we get the mother of all endomorphisms. Okay, so what's the mother of all endomorphisms? Well, when you look at this situation here, okay, what you will see is that, of course, you can pick this V to be any vector inside here. So you get a sub-object, okay? You'll always get a sub-object which contains any vector that you like inside this V. And you can study that sub-object up to isomorphism by replacing it with this one here. And how do you get this one here? Okay, so this one here comes quite easily from this kind of universal mother of all endomorphisms. This goes from C of t to C of t, and it's just multiplication by t. If you think about this, this is also what's known as the CT module, which is the regular representation of C of t. And if you know more module theory, then you know that you can apply a lot more theory here. Okay, so one of the things that basically we're talking about is that when you talk about modules, okay, every module is a quotient of a free module, and a free module is just a direct sum of the regular representation. Okay, so that's why this is the mother of all modules, essentially, over C of t, and hence this is the mother of all endomorphisms. And that's why this is this ring, polynomial ring, is the one ring that rules all endomorphisms. Okay, so let me just say some words about sample applications of this fact that you have this one ring that rules all endomorphisms. Okay, so really we want to study this ring. Okay, features of this ring and its module theory will tell us lots about linear endomorphisms. Okay, in fact, it will tell us everything. So I just want to give you one example here. In later videos in this playlist, I'll tell you more. But the first fact, for example, is that we know that this C of t is a principal ideal domain. So that means that every ideal inside here is generated by a single element. And what this tells you, and often this is also used in your second year linear algebra course, but it's not given to you from this more general perspective, is that it gives you the existence of minimal polynomials whenever you have a finite dimensional vector space and a linear endomorphism on that finite dimensional vector space. Okay, so why is that? So remember, another way to make a CT module V, okay, is that you have some vector space V, and you have a C algebra homomorphism from CT to endomorphisms of this V. Okay, so what's the endomorphisms of this V? So if the dimension of V is n, this is isomorphic to just n by n matrices in C. In particular, this is finite dimensional. This is a C algebra homomorphism, in fact, so it's going to be C linear. This is infinite dimensional, so it has to have some non-trivial kernel. Okay. That kernel psi, this might be psi, that's the psi that defines basically the module structure, how you do scalar multiplication by polynomials on here. Okay, so each polynomial, you can map it over here, and that tells you how you multiply by that polynomial on this elements of V. This is a non-trivial kernel, and remember it's a principal ideal domain, so it's generated by a single polynomial which is non-zero, and P. And that's basically the minimal polynomial. So we see here quite simply that the fact that C of t is a principal ideal domain gives you this minimal polynomial. Okay, so let's move on and see, well, you know, this is nice, but where can we go from here? Okay, so what happens if the dimension of V is infinite? Okay, that's what we're going to have a look at now. So here the story gets a lot more complicated, and the key point is that, of course, you can do a lot of this theory. This is fine. Okay, you can work over infinite dimensional vector spaces, and you can still talk about this as a CT module, and that's fine. But usually that's not what you want to do, and that's not the useful version for studying these linear endomorphisms. And the reason why is that when this is infinite dimensional, usually you want to allow some infinite linear combinations. So you would have seen this when you study Fourier series, for example, that you want to allow infinite series, so you have infinite sums instead. Okay, so what that really means is that this vector space V, you want to put more extra structure on it, which is going to allow you to form these infinite linear combinations sensibly. So this should be in other words, something called a Hilbert space. So hopefully you've seen this notion of a Hilbert space. If not, let me at least just give you a small example of one, which is little L2. And here this is essentially C to some form of C to the infinity. So you have just infinite sequences of complex numbers, A0, A1 up to and so on. Okay, so AI are complex numbers. And if you want to be able to manipulate this properly, so I guess you want to be able to form infinite linear combinations, okay, you also want to have things like an inner product, okay, on this space, and also and hence a topology. So what we'll do is we're going to assert that the sums of the square moduli of these is going to be finite, okay, and that's going to allow us to do the usual Euclidean inner product. That formula, except with an infinite sum, is going to work, okay, because we're not looking at arbitrary sequences. They have to go to 0 fast enough so that it doesn't matter when we do the dot product, okay, between any two such vectors, it'll still be something finite, okay. So in particular, this V will have a topology, and that's going to allow us to talk about limits when we try to do infinite linear combinations. And it also means that maybe we don't want to study arbitrary linear endomorphisms from a Hilbert space to a Hilbert space. We want to restrict our study. And so what we'll do is we're going to look instead at B of V, which is the set of continuous linear maps from V to V. It's written B here because it turns out this is equivalent to what's called the bounded linear maps from V to V. And the natural question here is, well, you know, when we were studying linear maps from V to V, especially in the finite dimensional case, as you do in second year linear algebra, so the one ring that really rules them all is the polynomial ring in one variable, okay? And the question here is there an analogous ring to this polynomial ring which allows you to study all these bounded or continuous linear endomorphisms? Okay, so that's the question. And the answer is unfortunately more subtle, and you have to add more conditions. So one of the things is that when you have such a continuous linear map, okay, just as when you have a matrix, you can talk about the adjoint of the matrix, okay, as in the transpose conjugate of a matrix, and that is usually denoted with a star, the adjoint. In this case, you want to restrict to the situation that T star equals T star T. So this is called normality of this operator T. And if you also impose this condition, then the answer is yes. There is now one C star algebra that rules all of these bounded linear endomorphisms. And what is that C star algebra? I've written here as C of CP1. So it's the C star algebra of continuous complex valued functions on the Riemann sphere. And basically having a look at this C star algebra, okay, and studying this is going to allow you to study these normal continuous linear endomorphisms. And this is the algebra, the ring that you want to have a look at for studying in this sort of analytical context. I hope you enjoyed this adventure in pure mathematics.